All right, so hello everyone and welcome to the second part of our pH measurement webinar series. Today focused on hygienic applications. For those of you who not attended, the first part that we had last week was really focused on general applications in the water, wastewater, and mining industry. And today we're going to bring the subject over the life science and food and beverage industry so we can understand a little bit more on how we can use the pH measurement into hygienic applications. Okay, just some very quick instructions on how to use the GoToWebinar. You can see on the right side of your screen there's a small box where you can download the presentation, and you can also type in all your questions and comments. By the end of this webinar, we'll have some time to answer some of them. If your question is not answered today, don't worry, we'll come back to you later on using the email you registered. Okay, this webinar is also being recorded, so you can watch it later on from our website. Very good. A brief introduction about myself. My name is Gustavo Queiroz. I'm the industry manager responsible for the food and beverage market here in Australia. I've been working with Endress+Hauser for nearly 10 years, most of this time in Brazil, where I worked with services and then product management, mainly focused on liquid analysis just before I moved to Australia. So let's get straight to the point. Before we talk about the technologies available for pH measurement in hygienic process, I just wanted to give you a quick overview on how the pH electrode works. We won't go as deep as we went in the first part of this series, but I really just want to highlight some of the key, let's say, topics and ideas we really need to have in mind to understand what makes a pH electrode suitable to be used in a hygienic process or not. All right. So here you can see the basic structure of a pH electrode. Every kind of pH electrode is composed for two main components. We have what we call the measuring cell. This is where the magic really happens. This is responsible to really measure the pH in your process. And we also have a reference cell, which is responsible to close the electrical circuit of the pH electrode. We have two main concepts here that we must have in mind. The first one is the material used, the technology used for that is sensitive to the pH measurement. On a standard glass electrode, we have a glass membrane that is sensitive to the pH, to the H+ ion, so it will measure the H+ ions difference between an inner solution and the outer solution, and it will create an electrical voltage that is proportional to the pH value. Okay, and the second one is the reference system, which has the aim to close the circuit between the inner part of the pH electrode and the outer part and make it get in contact with the glass membrane. Have in mind the importance of the junction. This is a porous material responsible to ensure the electrical contact between the inner and the outer part. And if it somehow gets clogged, the pH electrode stops working. Okay. And here we can see, for example, why you have to replace your pH electrode, let's say periodically, and why you have to do the maintenance and calibration. Inside the reference system, we have a very high salt concentration to really allow us to have a stable and accurate measurement. As soon as you install your pH electrode and the pH electrode starts to work, it will start losing part of the salt concentration to the outside due to the diffusion process. Okay, so have this in mind because we're gonna approach some of the concepts and some of the technologies we have available today to really increase the pH electrode's lifetime. That's very good. So when we talk about pH measurement in the food and beverage industry or in the life science industry or hygienic applications in general, we do have three different technologies available. We have the glass electrode, which is globally known as a potential solution. Unfortunately, not well accepted in the food and beverage industry due to the risk of breakage. And then to really solve this kind of problem, the market developed a second kind of technology called ESFET electrodes. These are made of plastic, so there's no risk of breakage. And we do have a third option called enamel electrodes, which are also very robust, and we're going to talk a little bit further later on in the presentation. Okay, so these are the three main technologies for hygienic applications, and let's go a little bit deeper into each one of them. Glass electrode application. So since glass is not well accepted in the food and beverage industry, we have one application focused on the life science industry, which is the fermentation or bioprocess in general. Okay, so whenever you have a fermentation process or a bioreactor, usually the pH is a key performance, is a key variable to really ensure the yield of your batch. So the microorganisms need to work under a very narrow pH range if they really want to achieve. Sorry, we're having some comments here. Oh, good. Sorry about it. So pH measurement in the life science industry, mainly for fermentation and bioprocesses in general, is a key aspect is a key control parameter for the yield of the process. Okay, but the life science industry has several, let's say, challenges we need to cover, or we need to go by to overcome if you really want to have a very reliable measurement, especially regarding the SIP, which is a sterilization. So the pH electrode must be able to be exposed to very high temperatures and still be able to do a very proper measurement after that. And also the CIP, so the sensor must be able to withstand high chemical exposure, high temperature due to steam, and after all of that must be able to ensure a proper measurement. And we have developed the best electrode for this kind of application, which is the CPS 171D. And we have some very interesting resources to really increase your productivity and ensure that you have a very stable and reliable measurement. The first one is the MemoSense connection. So all Endress+Hauser liquid analysis sensors are already integrated into the MemoSense technology. So all the information the sensor is producing, so all the voltage that is created that is proportional to the pH value in your process is being converted into a digital signal and being transferred to your transmitter as a digital package. So we can ensure that the pH value that it's at the tip of your pH electrode is really the pH value that you're reading on your transmitter, and it's been sent to your PLC. This is just one of the aspects. The second one is the special glass membrane that was developed to really withstand the very high temperature variations caused by steam, and also to withstand the chemical attack caused by, especially by the alkaline step of your CIP. And you can see on the charts on the top that after several SIP cycles, the CPS 171D, which is this handsome electrode here at the bottom, kept its characteristics in a very robust way. So it's really a very powerful resource if you really want to increase and improve your process, and it's completely hygienic. Just a brief comment that I forgot to mention. All the pH electrodes need to have what we call a ceramic diaphragm. So these are the poro materials that helps that closes the electrical circuit between the inner part of the electrode and the outside. And we have very tiny pore sizes, usually with the pore size smaller than 0.1 micron, to really avoid any kind of bacteria or microorganisms to go inside the pH electrode and consequently turn this into a potential source of contamination of your process. And to really help and avoid the diaphragm to be clogged, we also have what we call the pressurized gel reference. So it pushes the KCl out of the electrode, ensuring that the diaphragm is always clean and able to measure. Okay, that's very good. Here we have some examples on how the pH electrodes need to be installed. You should always, you must always install your pH electrode with the right assembly. As you can see here, this metal assembly, they are protecting the pH electrode. If you take a look on how the pH electrode really is, The process connection we have here is not hygienic, and it was not designed to be used straight into pipes. So you always need this process assembly to ensure that your pH electrode is installed in the right way, and also to protect the sensor body. Awesome. Let's go to the second part of our pH versions. The second one is called ESFET electrode, and here we can see a couple of differences compared to the standard glass electrode. The main difference here is on how the sensor actually works. Okay, when you have a glass membrane, when you have a glass electrode, you have a glass membrane that is selective, or you have a selective glass membrane which is exposed to a chemical reaction, getting H+ ions from the outside, bringing to the inside, and vice versa. With the ESFET electrodes, we have a different concept. Instead of having a selective glass membrane, we have a field effect transistor that is sensitive to H+ ions. And we install this at the tip of the sensor. And here we don't have any kind of chemical reaction. We just have an electrostatic effect over the chip. So when you have, as more H+ ions, so as more, the higher or the lower the pH you have influencing this area, the higher the current flowing through the transistor, and the transmitter is able to get this current changes and convert it into pH. So this is not only this is not one of the this is not only the only advantage of the ESFET electrodes. We have a second one, which is the plastic body. So instead of using a glass body, we have a polymer body called PIC, which is a very strong material, mechanically and chemically speaking. The NASA used to use this kind of material in their spaceships. I'm pretty sure SpaceX also using on theirs, because it's a very strong material and it has very nice chemical and mechanical properties. So you can use this kind of sensor in the food and beverage industry without any risk of breakage in your process. So these are really interesting resources. And we do have the same concepts that we also had for the glass electrodes, which is the ceramic diaphragm and the pressurized or the gel filled reference system. So this is really one of the interesting resources we have for the food and beverage industry. Here we have one application example to really identify contamination, especially during the bottling phase. pH measurement is a very interesting variable you can use for quality control. And in this specific application, we're measuring the pH of beer. Okay, so if you have any kind of contamination due to chemical from CAP, for example, pH is a very reliable variable you can use to identify it. And just have one thing in mind, for pH electrodes in general, the alkaline step of your CAP is very, very stressful to any kind of pH electrodes, from glass, ESFET, and even the enamel pH electrodes. So we always must have in mind, and if you really want to extend the lifetime of our pH electrodes, we always orient to use a retractable assembly just like this one. So the idea here is you can measure the pH of your beer or your product in general, and whenever you're doing the CAP, which is a very aggressive exposure to your pH electrode, you can retract it. You can retract your pH electrode and run the cleaning in a separate chamber with a less aggressive material. So this is basically what we can do to really increase the lifetime of our pH electrode. So here is the solution we often promote for the food and beverage industry, the ESFET electrode retractable assembly. And if you really want to reduce labor resources, you can always have an automatic cleaning and calibration system. As I mentioned before, the reference system has a very high salt concentration, and as soon as you place your pH electrode in your process, it will start to drift. It will start to lose the concentration due to diffusion. And one of the ways, if you really need a very reliable and accurate measurements, you can always rely on an automatic cleaning system, automatic calibration and cleaning system to calibrate your pH electrode as often as you want. So these are really This is a really powerful tool if you really need a very reliable measurement, okay? The third technology we have for pH applications in hygienic environment is using the enamel electrode. Here we have a couple of differences if you compare at least this kind of electrode with the ESFET and the glass electrode. The first one we can see is that the sensor body is made of stainless steel, so the sensor is really, really robust. And we also have a very interesting concept regarding the measuring area. So instead of having a glass or an ESFET, we have a ceramic called enamel, which has nearly the same composition as we have in our teeth. And we have a very thick enamel layer, so the sensor can really withstand even the harshest conditions. And one thing that's really, really important here is, at least compared to the glass electrodes, you have a very, let's say, bigger measuring area compared to any other sensor technology. So these make this kind of technology suitable to measure the pH even in very high viscosity and very sticky media. If you have the same application and you try to do this with ESFET electrode, you will always need a cleaning system to ensure that the sensor is not clogged at all. So this is a different concept we have for measuring pH. One of the main advantages of the enamel electrode is that it's the only pH electrode that has the process connection attached to the body, okay? And this one is not considered a consumable. If you have any experiences with pH measurement in general, you know that you have to use your pH electrode for 1 year or even less, depending on the application. You have to, after a while, you have to take it out, throw it away, and replace it for a new one. While the enamel electrodes are considered an asset of your process. You just install it there, and it can work for a longer period of time. And we even have some case studies, success stories using this sensor where the customer is able to calibrate it once a year. So it's really a very powerful technology if you really want to really reduce your maintenance and bring the lab measurement to your process in general. Okay, here we have a couple of examples to summarize the use of the enamel electrode. So as I mentioned, very high viscosity applications and very sticky media such as mayo and ketchup. The sensor works extremely, extremely well. You can see the sensor is installed here, and we have a KCl reservoir installed here at the top. So this one is pushing the KCl into the pH electrode, and that's one of the reasons why the sensor can last longer compared to glass electrodes and ESFET electrodes. Okay, and just a couple more applications. One of them in hydrolyzed starch, which is also a very high viscosity medium. And the second one in syrup, which is a really tricky application. Both of them are working perfectly fine. Okay. Awesome. So this is really what I wanted to share with you regarding the hygienic technologies we have for pH measurement. So we have the glass, the ESFET, and the enamel electrodes. But there is also one topic that is really, really relevant in the food and beverage and in the life science industry, which is the differences between lab and process measurements. I'm pretty sure if you work with pH measurement and if you try to do a comparison one day of your life, I'm pretty sure you notice that it's very hard for you to match all these measurements. And we have 3 main factors that we separated here to really aware you and to show you how you can minimize them and really bring your comparisons as close as possible, right? Factor number 1 is the temperature between the lab and the process. The process pH electrodes will always measure the pH at the process temperature. So if you're measuring a pH at 60 degrees, the value you're seeing on the display is the pH value at 60 degrees. If you take a sample, bring it to your lab, cool it down to 25 degrees and do another measurement, you will always observe different values. Okay, this is let's say the top 1 source of differences between these comparisons. But there's a way for us to solve this kind of problem. And here we have a table that explains that we can see somehow the influence of temperature in the pH values of hydrochloric acid. So in hydrochloric acid with a very low concentration, a 10 degrees variation won't give you, let's say, won't give you any pH variance. But if you take any sodium hydroxide or even the buffer phosphate, which we use for the pH calibration, you can start seeing some significant changes due to temperature variation. And always have in mind that the pH measurement is based on a log scale. So whenever you have one pH unit variation, your H+ concentration varies 10 times. So it's half a unit, 0.3 is often a very significant change. And to really help you guys minimize this kind of problem, all Endress+Hauser transmitters, such as the CM44X and the CM42, they all have the possibility to compensate. They all have the possibility to receive a temperature table relating the temperature influence on the pH. So you can insert this kind of information on a transmitter, and the transmitter will give you the information corrected or converted to 25 degrees, which is the same temperature reference used in the lab. So this is a factor number 1. Good. Factor number 2, that's the sample contamination. So depending on your sample characteristics, for example, if you have water for injection is the kind of sample that is very easily prone to contamination, especially with carbon dioxide. If you breathe over water for injection, the carbon dioxide from your breathing will turn into carbonic acid, and it will lower the pH. So it's often a little bit hard for you to keep all of these things in mind. And to really minimize this kind of problem, we do have a very interesting solution, which is called the Liquiline Mobile, which is this little guy right here. So it works with MemoSense technology, completely free of metals on the sensor. And as soon as you connect the sensor, it will recognize and will start measuring straight away. Okay. Also a very interesting resource, and also works with any MemoSense sensors that you connect on it. Awesome. And then we're coming to the last factor that will also influence on the comparison between lab and process, which is different sensors used for these comparisons. So if you're using different technologies or different sensors, you can have a different glass selectivity, you can have different response time, the signal processing may change, even the temperature compensation may not be done the same way. So as a hint for us as a producer, and we receive this feedback very often from our customers, always try to use the same technology in the lab and in the process. This is a very important thing for you guys to have in mind if you really want to reduce and minimize the errors when you're doing this comparison between lab and process. And that's really what I wanted to share with you today. And now I think we have a couple of minutes to answer some of the questions. And I would just ask for my colleagues to share with me the questions they have.
All right, thanks, Gustavo. The first question we have is from Michael. He asks what the disadvantages of ISFET sensors compared to glass are.
What are the disadvantages of ISFET sensors compared to glass? Okay. When the first ISFET sensors were launched in the market, they had a very low resistance, especially to CIP exposure. So the first generation of ISFET electrodes from Endress+Hauser, whenever you expose it to a CIP applications, sodium hydroxide at high temperature, you will reduce the lifetime of their pH electrode to some hours or a couple of days. Now we have enhanced the performance. Now the ISFET electrodes are able to withstand several CIP cycles, but still the glass electrodes are a little bit more robust to CIP. So that's the glass electrodes still have still has the advantage regarding CIP cycles over the ESVAT electrodes. That's why we use some of the resources I mentioned, such as the retractable assembly and the automatic cleaning and calibration. Okay.
Thanks, Gus. We have another question from Luke. This one is around the number of SIP cycles that a CPS 171D can send.
Okay. There is not a maximum SIP number of cycles that is estimated, because this varies from industry to industry depending on how much time you consider as an SIP or not. But we've made some trials using 30 minutes exposure to steam at 140 degrees, and the sensor could withstand more than 50, 60, or even 70 SIP cycles without any changes, without, let's say, very significant changes on its performance. Okay.
I have another question around the KCl reservoir.
Yeah.
How often do you have to refill this KCl reservoir, and how much KCl is used, like on average per day?
Okay. Usually the KCl is consumed over months. We usually orient to have the pressure on the KCl reservoir 2 bars or 1.5 to 2 bars above the process pressure, and it usually takes around 9 to 11 months to consume 1 liter of KCl. So that's the number we have for the KCl consumption in general.
Have another question now. This is around a particular sticky substance, like for example liquid candy. But how do I make sure that my pH probe, while it's measuring in solution, is kept clean? What's the best way to keep something like this clean?
Okay, so as we have two, for very sticky media, we have 2 basic applications. Okay, we have the enamel pH electrode, which is really powerful because you have a very big measuring area. So whenever you have product in contact with the enamel surface, it will give you the measurement straight away. But you must have the proper cleaning afterwards if you really want to have an accurate measurement. If you have a very sticky application, which is really hard for you to clean, we always will recommend the use of a retractable assembly with the proper cleaning. So the pH electrodes can measure for a couple of hours, can be retracted, cleaned, and then come back to your process later on without any risk of contamination. So these are basically the 2 approaches we have, and we often pick one of them. We often pick the one we need based on a case-by-case analysis.
We have another question now around the enamel probe. If I shut down my plant, let's say overnight, is it okay to leave the enamel probes in the process? Let's say the process stops, is it okay to leave them in there overnight? Or do I have to take them out and store them away?
Okay. The glass that's a very good question. The glass and the ESVAT electrodes must always be stored in a wet place. They must be kept moisture to really ensure that you won't have any kind of problem. The enamel pH electrodes can be stored dry. So if you have any kind of problem with your plant and the sensor gets dry, it's not a problem at all. But if it takes more than 2, 3, or 4 days for you to restore the pH measurement, you need to do what we call the reactivation. You need to expose the enamel surface to water for a period of time to have it, let's say, active and ready for the pH measurement.
All right. That's all the questions we've got so far.
That's really good. So if you have any other questions, please just let us know. We're more than happy to answer all of them. And well, I guess that's it. So thank you very much for your participation, and see you on the next webinar.